so that the right side is a little bit more anterior and the left side is a little bit more posterior. Okay, but this is a coronal cut. Have you ever seen those people in the like cafeterias and stuff wearing those like hat things on their heads? You know what I'm talking about? That's what this looks like, doesn't it? But those are actually what? Lungs. That's not somebody with a hat on their head. Okay, so we got 2 lungs, and we have the 4 chambers, right? So this would be the right atrium. Now this heart would be like you're looking into me. It's been cut coronally. You're looking into my body. Do you follow?
Yeah.
Okay. So this is the right atrium,
left atrium, right ventricle, left ventricle.
Okay. They use colors to indicate oxygen levels. I wouldn't use the colors that they use, but it was already done when I got here. So what would gray indicate probably?
Blue.
It would be like blue, right? It may have been blue when they first did this. It's been around long enough that the blue may have faded to gray. I really don't know. But I would have used blue. And then here where they have this kind of orangey red, I would have used probably more like a fire engine red. So blue indicates deficient in oxygen, right? And red indicates oxygen rich, okay? All right. We have a wrapper around the heart, and it's not LL Cool J, so that must be
pericardium.
Okay. Okay, so I think we're ready to start. Like I said, I'm going to do a little bit of physiology with you. Okay. So what would this vessel right here coming to the right atrium be? Superior vena cava. Okay, so blood is going to come from the superior vena cava into the right atrium because of gravity. You don't have to do any pumping. Gravity will pull stuff down, right? So this blood will just drain in here. That's pretty cool. That doesn't take any work. It does it like all by itself. We also have blood coming from this vessel into the right atrium. This must be the inferior vena cava. Does blood go up against gravity?
No.
Not usually, not on its own. So how can we get blood to come up into the right atrium through that vessel?
You need the semilunar valves to do it.
The semilunar valves prevent backflow, but they don't make it go up. Pressure. And where do we get the pressure? Skeletal
Muscle
pump. We talked about that. Remember the thing we were talking about? Yes, no?
Yeah.
Okay. So when a person's walking around, their muscles are squeezing their vessels. The valves, the semilunar valves, prevent the stuff from going the wrong way, and the pressure causes it to come up. That's the only way it can go then. Okay? And so that comes in here. We're missing an opening. There should be an opening right there, and that would be the coronary sinus. Okay? All right. Now, there aren't any pectinate muscles drawn in this picture. I don't know what to tell you. I didn't draw it, so somebody didn't put it in. There also is an oval flat depression. If I were to reach into these 2 atria and bring my fingers together, posterior to this structure, there'd be a place where you could just feel like all you had was a glove there. What would that be? Fossa
ovalis.
Okay. All right. So this blood then goes from the right atrium down into the right ventricle. In doing so, it passes over the tricuspid valve, which has these funky-looking things attached to it. They're chordae tendineae, and they're attached to these pimples.
Papillary
Muscles. You can see the tree roots down in here, and those tree roots are trabeculi carni. Okay. You'll notice that the atrial wall is thinner than the ventricular wall. And you'll notice that the right ventricular wall is thinner than the left ventricular wall. So those things are pretty accurate. All right. Okay, and then there is a place in the right ventricular wall that's self-excitatory. It's called the SA node. Some of you might have known that, right? And so it excites itself. Some of you may even know people like that. Not that there's anything wrong with that. So when that's called the SA node, when it stimulates the atrium contracts. Okay? And so when it contracts, oh, and what I didn't tell you, I should have. 75 to 80% of the blood that goes into the ventricle just goes in without any pumping. Now that actually requires that we talk about something for a moment. Most of you probably thought that the heart was a pump. And yet I'm telling you that this heart is sitting here relaxed while this blood is going in here, suggesting that it's not pumping at least a part of the time. So there are two reasons that the heart has to relax. One reason that it has to relax would be
because if it was constantly pushing or pumping,
yeah.
it would overwork itself.
Yeah, it could fatigue. So it has to recover from all the work it's doing. So that's one thing it needs to rest for. What's the other reason?
Let blood in?
Yeah, it has to fill with blood, right? If the blood doesn't come into it, it won't have anything to pump. So if you take a turkey baster that's all full of stuff and you squeeze it, stuff will come out, right? You're pumping stuff out. But if you never let go of it, it'll only come out for a while, and then it won't pump anymore because there's nothing to pump. The same thing would happen with the heart. So when the heart contracts, blood comes out, but it won't come out forever. Eventually, it'll mostly be out, and if you want to pump anymore, it has to fill. Everybody follow that? Okay. So, we got the 75 or 80%. The SA node causes the right atrium to contract. It contracts, sends the other 20-25% into the ventricle. And then the right atrium starts to relax. And just as it starts to relax, the ventricle contracts. And when the ventricle contracts, pressure in here is going to build up. And the blood's going to try to go right through that opening back into the atrium. Because you understand, blood does not care where it goes. If there's a hole and it gets pressure put on it, it'll come out. Whether it's supposed to go there or not, it doesn't care. It just goes where it can, right? Everybody follow this?
But the valve is closed when it does that.
Not yet. Not yet. So when the blood starts to go that way, it's going to push on the valve just like the wind on the door with the little kids. Remember we talked about that? And it's going to push that valve closed. And when that valve closes, it's going to pull on the chordae tendineae, and the chordae tendineae are going to pull on the papillary muscles, and the papillary muscles get stretched. And what do papillary muscles do when they get stretched? They contract against the stretch, so they pull back. And when they pull back, they don't let the valve go too far. If they didn't do that, or if you cut these valves, cut these chordae tendineae, the valve would blow right back into the atrium. Everybody follow?
Yeah.
Okay. That would be a prolapse valve. All right, so now this is closed, and the ventricle is trying to contract, but there's no opening for the blood to leave by, because that just closed off. And at this point, this is closed. Now, what does that look like? Short pockets, right? Remember I talked about that?
Yeah.
So short pockets, what it looks like short pockets? Semilunar valves. So this must be the pulmonary semilunar valve, okay? And that leads to the what? Pulmonary trunk, which is blue because it's oxygen deficient blood. Now, the question is, oh, and I asked, what does that look like? And this woman a couple years ago said, looks like your butt. So maybe, I don't think that's going to help with the whole valve thing though. So I would go with the semilunar valve thing, right? In the short pockets, right? All right, so let's now talk about why that's closed. On the last heartbeat, the pressure in the ventricle got high enough so that it opened this up and the blood went into the pulmonary trunk. When the blood goes into the pulmonary trunk is going to stretch like a tire, a bicycle tire that you're pumping up. You take a bicycle tire and pump it and it will stretch, right? Some of you have seen this kind of thing happen maybe.
You actually blow it up if you stretch it enough.
Yeah, we're going to try not to do that. So, when that pulmonary trunk stretches, what's it going to do? We talked about this. Contract against the stretch, because smooth muscle contracts against the stretch. Remember I talked about that? Okay, so it squeezes, but it can't win. Because see how thick its wall is? And see how thick this wall is? This one's going to have more pressure than this can create. So it stays stretched. It's like a balloon full of air. And it can't cause the blood to go back toward the ventricle because it's not strong enough. And then the ventricle relaxes. When the ventricle relaxes, the pressure from down here drops. And when that happens, this thing's still stretched with all this blood in it. This is like the tube of toothpaste. Did any of you try that at a friend's house? Oh, you don't have friends. Any of you that try at a...
I didn't do it at my friend's house because I didn't want to upset my friend.
You go to a stranger's house. So.
Yeah, good.
So what happens when you squeeze the toothpaste and both ends are cut off? Stuff comes out of both ends, right? So when this vessel squeezes back now, because it's not being opposed, the blood starts to leave. Some of the blood's going to go toward the lungs, some of the blood's going to go back toward the right ventricle. Are you with me?
Yeah.
Okay. When it goes back toward the right ventricle, it pushes that semilunar valve closed. That's a sure pocket thing, remember? Blood goes the wrong way, it catches it, they deploy like a little parachute. So this is closed off and it can't go back to the right ventricle, and the pressure holds it closed. And the blood then, as the pulmonary trunk goes back to its original shape, is being ejected toward the lungs. Are you with me? What this means is that even though the heart isn't pumping, the blood's still moving. And the blood's still moving because the vessels are making it happen. Okay. And about the time that the pulmonary trunk gets back to its original shape, the ventricle's contracting again, the pressure in here isn't that high, and the ventricle blows this open and the blood goes in there and the pulmonary trunk stretches and we start all over again. Okay? So you follow that dynamic. Okay. So now we've got the blood out of the heart. It goes to the lungs, it picks up oxygen, comes back by way of the 4 pulmonary veins. There are two, comes into the left atrium. Same thing on the left side happens that happened on the right. Oh, by the way, we can't see the moderator band because it's out here on the ventral side. With me?
Yeah.
Okay. So about 75–80% of the blood that's coming into this left atrium just goes into the left ventricle. To do that, it goes over this valve. What's that valve?
Bicuspid.
That's a bicuspid or mitral valve. And it has chordae tendineae, and the chordae tendineae are attached to papillary muscles. Okay? So 75–80% of the blood just flows in here, and then when the SA node causes this to contract, signals come to this, and this contracts at the same time. So the left atrium contracts, it sends the last 20–25% of the blood in there. Okay? And then as it relaxes, the left ventricle starts to contract, which causes the blood to try to go back through this hole. And when it does, it pushes that valve closed, right? And the chordae tendineae get pulled with the valve, and they stretch the papillary muscle. Papillary muscle contracts and pulls back, prevents the valve from collapsing. We good so far?
Yeah.
Okay. Pressure builds up, and this semilunar valve eventually gets pushed open. Blood goes into the aorta. When the blood goes into the aorta, it stretches. The aorta contracts against the stretch. It doesn't win because it's weaker than this wall, which is huge. Okay? Eventually, this relaxes. When it does, the aorta stretches, so it contracts, and the blood comes back and closes this valve, and then the rest of the blood goes out to the body. Okay? So the same thing's happening on this side. The blood is always flowing. It doesn't ever really stop, which is a good thing. You don't want the blood to be surging through the vessels. If it goes and then stops and goes and stops, that would not be a very efficient way of getting oxygen to your tissues. So having it move all the time is really kind of important. We have the pointy end of the heart.
Apex.
Okay. Oh, and one other thing up here. We have this bridge that goes between the pulmonary trunk and the aorta. What's the bridge?
Ligamentum.
Ligamentum
Arteriosum.
Remember Harry Potter, right? Ligamentum arteriosum.
Okay.
So that's that. And that used to be a functional vessel. We're going to talk about that during the embryonic phases. While you're a fetus, that transfers blood from the pulmonary trunk to the aorta. But in the adult, it should not. It squeezes off and it becomes a ligament. I think we covered everything, did we? Oh, no, there's one other thing. So there's this groove right here between the atria and the ventricles. What's that groove? Nope. What's the groove between the atria and the ventricles?
A sinus?
Not a sinus. Oh, the sinus sits over it.
Oh, the cardiac.
No.
The one that goes around?
Yeah, the one that goes around. The coronary sulcus.
Oh, coronary.
Okay. So this is, I think of the coronary sulcus as where an adult male would wear their belt. You know, it gets narrow there. Are you with me on this? This is the narrow piece. If it's where an adolescent male, the belt would be here, right? So that they can't walk. But for most adults, it would be up here. Now, what you're going to see on the hearts you're studying today is that's where you can see the coronary arteries and the coronary veins. The coronary arteries and veins are both tubes. They're not going to have any color in them because there's no dye in these hearts. So the question is, how can you tell which one's the artery and which one's the vein? Okay. The artery has thicker walls. The veins have really, really thin walls. So on a lab practical,